It's question 50 from 4.3, and it's h of x is equal to 5x cubed minus 3x to the 5 to 5. Yeah.
Okay, what are we trying to do? What was the question?
I believe it was. Let me just go back to the textbook. 1 second.
So is it from WebAssign? It doesn't matter where it is, but what are we asked?
It's from the textbook.
Okay, so we're asked to graph everything, or is that the question?
Yes, we were asked to graph everything.
Okay, perfect. Awesome. Good. Can anyone give us the domain of this function?
All real numbers?
Yes, it's a polynomial function. Thank you very much. All real numbers. Perfect. Okay, so the next step is I know I saw that. I'm just trying to push these cables to the side, these cords. I saw that. Sorry about that. Good. Okay, so first of all, I look at this function and I see it has degree 5. I look at it and I see that it's not in descending order. And I looked at and I see that I can factor out negative x to the third, and I have 3x squared minus 5. So I already see those immediately. I factor out x cubed. I have 3x squared minus 5. You can always check, go back and distribute, and you get this, and you get that. So now when I set, sorry, I didn't get the chance to do anything with the derivative. So when I set h prime equal to 0 to find the x-intercepts, I have to have 5 solutions. Well, it happens that 3 of them are the same. So all these 3 are the same, x equals 0. The other 2 come from 3, x squared minus 5 equals 0. I move 5 and divide by 3, so x squared equals 5/3. And I have to take the square root. So one solution is the square root of 5/3, and I have to approximate it because I don't know where to put it in the table, right? And the other one is definitely the negative, the square root of 5/3, and I have to approximate it. Also at this moment, right now, before I write anything or put anything in the table, I realize that h of x is odd. How do I know that? Because h of negative x will give us negative h of x. So if you replace x by negative x in here, and let's do that, so to show that, h of negative x, we get 5 negative x to the third minus 3 negative x to the fifth. But this stays as negative because it's power 3, and this stays as negative because it's power 5, but it has a minus in front, so that will turn into plus. And this happens to be exactly negative h of x. So if you take the original function and multiply both terms by -1, you will recover this. So I'll make myself a note, maybe in a different color. Hey, don't forget, make sure that if something happens and you don't get an odd function or symmetric points from the third to the first or from the second to the fourth, something is terribly wrong. The function is odd. It has to be symmetric with respect to the origin. Okay, so for this, I'm not going to share my screen. I'm just going to take the square root of 5 divided by 3, and I get 1.3, roughly, approximately. So this is 1.3. This is negative 1.3. So I have to have in the table 0. I have to have 1.3 and negative 1.3. Again, be prepared that the table, especially I'm using markers, right? If the table gets too crowded, I will immediately go landscape so that I can explain what I'm doing. Because it's possible, especially for polynomial functions. So we'll see. So negative 1.3 and 1.3, 0 and 0. And I need to find the limits. But I know that the limit, let's write it, limit of 5x to the third minus 3x to the fifth when x approaches infinity. This is the most powerful term. It has a negative in front, so infinity to the fifth power with minus in front must be negative infinity. And the other one, limit as x approaches negative infinity from 5x cubed minus 3x to the fifth. When I plug it in, this is positive. Because this one means nothing. It's too small at infinities. So then I have at positive infinity, negative infinity, and infinity here. Now this is done. I cannot find anything more. The function cannot disclose to me anything else. It disclosed the x-intercept and also the y-intercept and also 3 x-intercepts. And it gave me the limit at negative infinity and the limit at infinity. This is it. Now I have to continue with the first derivative. Let's stop for a moment and see if this is clear. See if you have any questions or if you want to say anything. So let's analyze this. Anyone would like to say anything?
Do we always have to figure?
Yes.
Do we always now, when making this, have to state if the function's odd or even?
Yes, absolutely. It's part of the list. It's the symmetry.
Okay.
Yes.
Okay.
If you go back to the list that I like to call infinity, well, of course it's not infinity, but there are a lot of things in there. One of them is symmetry, and we always put it somewhere in the table. It doesn't really fit anywhere, but I put it on the side where the function is, so I don't forget. Okay, now I can move on to the first derivative. So for the first derivative, can anyone give us the first derivative? Here's the function, 5x to the third minus 3x to the fifth.
15x squared.
Yes, perfect. Minus
15x to the fourth.
Excellent. So of course I will immediately rearrange it in the correct order. I will immediately factor out the negative 15x squared and get x squared minus 1. Why? Because I will set this equal to 0. Why? Or to undefined, which makes no sense for a polynomial function, but I have to have that in the back of my mind. Why would I do that? Why am I thinking in these terms? What for? Why would I ever think of finding or setting equal to 0 h prime or undefined? What for? What am I
in order to find any maximums or minimums?
Yes, exactly. So the first step is if I find any critical number or numbers. Yes, when I set this equal to 0, it's very clear. It's degree 4. I have to have 4 solutions. So 2 solutions will be 0, and one of them will be 1, and the other one will be negative 1. 2 solutions from here. 1 solution from x squared minus 1, positive 1, and negative 1. So I'll have to put these in the table, as I was expecting. Okay. Now I have to study the sign. But I refuse to study the sign of 15x squared. It's a waste of time. It's always positive. What I will study the sign is of x squared minus 1 with minus in front. Okay? So if I plug in negative 10, this will be positive, but it will be negative afterwards. If I plug in negative 0.5, this is negative with negative, which is positive. If I plug in 0.5, again positive. And if I plug in 10, it will be negative. At this point, I'll say stop and make sure that these two rows go in sync. If they don't, I'll say, uh-oh, back to the drawing board. So let's try. From infinity to 0, yes, that's okay. Ah, I have to find these two values first. So, and they have to be opposites because the function is odd. So when I plug in 1, 5 minus 3 is 2. When I plug in -1, it has to be -2. Okay, so this will be positive. Let me see again. 5 minus 3, yes, that's correct. So this was, yes, this is -5, and this is +3, as expected. It has to be -2. There is no need to check, but I like to check. Okay, it's an odd function. Good. So now, again, I'm trying to make sense of the information. From infinity to 0, yes, that's okay. Correct. That's what the derivative tells us. From 0 to -2, yes, that's correct. From -2 to 0, yes, that's correct. From 0 to 2, yes, that's correct. And from 2 to 0, yes, that's correct. And from 0 to -infinity, that's correct. So the sign of the derivative and the numbers we obtained work well together. That's my check for now. First check. Okay, now I have to identify what type of point is -1, -2. What type of point is 0, 0, and what type of point is 1, 2? Can anyone tell us and help us with -1, -2? What type of point is that?
Inflection point.
We have not discussed the second derivative. The inflection points do not come into play at all till the second derivative. We did not get to the second derivative. Yes, because see, look at the arrows and look at the sign of the derivative. So this is a local min. Perfect. What about 0, 0? Is that a local max or min?
No.
No, because the derivative does not change sign. Perfect. What about 1, 2? What type of point is 1, 2?
It's a local max?
Yes. Look at the arrows. And that's for the first derivative, and then 0, and then negative. So this is a local max. Okay, or you can call them relative if you want. This is it. I can't find anything else. Now I have to move on to the third row, which is, or the fourth row if you want, but the second derivative. Yes. So I do not differentiate this, of course. I will differentiate this. That's the easiest. So can anyone give us the second derivative? I'll copy the first here. Yes.
Minus.
Careful. So we bring down 4, and we have 60, right? So 4 times 15 is 60, and then this, we subtract 1 from the power, which is 4 minus 1. And then plus, yes, here we do have 30x. Okay, so I immediately factor out negative 30x, and I get 2x squared minus 1. So one more time. The first derivative was negative 15x to the fourth plus 15x squared. Oh, you differentiated this one. Okay, I'm sorry. I see. So, but I went here and you went there. That's fine. We got the same thing. Good. So negative 60x to the third and plus 30x. We factor out negative 30x, and then I have 2x squared minus 1. So the second derivative, 0 or undefined. There is no discussion there. It's a polynomial function. Good. So then degree is 3, so I have to have 3 solutions. One solution from here, which is 0. And this one is 2x squared equals 1 or x squared equals 1/2. And we have to take the square root. So as expected, I may have to redo my table because it will really be crowded in there. Okay, so let's see what is the square root of 0.5. 0.7. So this is 0.7 and negative 0.7. It's getting very crowded in here. Negative 0.7 and 0.7 and 0 and 0. Okay, so I have to study the sign of the second derivative now. And I also have to plug in the function 0.7 and 0.7. So at this point, I'm going to share my screen and just go directly to the graphing calculator to put that 0.7 in there. They have to be the same but opposite numbers because the function is odd. So we had 5 x to the third and then minus 3 x to the fifth. So in here, I have to plug in the 0.7 and see what I get. 1.2. So this is 1.2, and this is negative 1.2. And finally, we have to study the sign of the second derivative. So here's the second derivative. Messy. Okay, so let's give it a try. With negative 10, this is positive, and this is positive. I'm going to plug in, I can't plug in 0. Okay. Oh, I forgot 0, 0. Okay. Okay. Now I have to plug in a number between negative 0.7 and 0. No, I'm not going to do that by hand. I'm going to share my screen and put in the second derivative in here, which was negative 30x. And then parentheses 2x squared minus 1. And if you don't need to see this, that's fine. We can de-highlight that, and we will only see this. So I plugged in negative 10. I plugged in, what was it? Negative 0.5. Not yet, I didn't plug it in. So it's negative as expected. And then I plug in, there is no need, but let's say I plug in 0.5, and it obviously has to be positive. And then I plug in 10, and it will have to be negative. So my table did get crowded. So opening up, opening down, opening up, opening down. So now, can anyone tell us what is, very difficult to see, I know, negative 0.7 comma negative 1.2?
Inflection point.
Yes, awesome, yes. What type of point is 0 comma 0?
Inflection point.
Absolutely, thank you. And what type of point is 0.7? Of course, the function is odd, has to be the same thing. It changes sign again, so inflection point. So one more time. When we analyze the function and then the first derivative, then we identify local max, local min. For inflection points on concavity, we have to analyze the second derivative. We cannot draw any conclusions where the inflection points are till we analyze the second derivative and put the points in. Now, looking at this, I let you decide. Is it clear enough or not really, and I have to redo the table? I can redo the table, it will not take too long. But if you say, oh, I think I got it, I will not redo the table. Let me know if you want me to redo the table. It will not take long if you say so.
Could you quickly switch to the second paper? The back of this? Yes.
Is this okay?
Yes, I'm just copying it down.
Okay. So since no one said that I should redo the table, I don't care for anything else. That's all I need. That's it. Okay. I don't know how to put it here. Maybe I should do this.
I
Okay.
got it.
Is this okay? Good enough?
Yeah, I got it.
Okay.
Thank you.
Thank you. So this is all I need. Just this table. I don't care for anything else. Nothing else means anything to me anymore. Okay. So the biggest is 1.3, and here the biggest is 2. So I'm going to say this is 1, 2, big units. 1, 2. 1, 2, 1, 2. Okay. So first the points. I have to plot the points. Negative 1.3 is somewhere here. Negative 1 comma negative 2 is here. 0 comma 0 is here. Negative 0.7, negative 1.2, somewhere here. And I only have to translate this in the first quadrant. Again, 1.2, 0.7, 1.2, 1, 2, and then 1.3. So now careful, step by step from left to right. The function comes from infinity, opening up to the x-intercept. Okay, fine. Continue to decrease, still opening up to the local minimum. Okay, fine. Now it increases to the point of inflection. Okay, fine. It changes concavity, opening down, going up to the origin, where it changes concavity again because the second derivative changes sign, and that's an inflection point. Okay, fine. And it goes up, opening up, goes up, opening up to the next point of inflection. Fine. I should just copy what I have here, but that's okay. Now, it's an inflection point again, changes concavity and goes to the local max. And then crosses the x-axis, opening down all the way to negative infinity. Very nice graph. So this is f of x. See, 3 pages ago, who cares? Nothing else matters at the table. So now I can copy 5x cubed minus 3x to the 5th.